All right, guys. Good morning. Good morning. We're going to go ahead and get started here. Our focus for this week, if I pull up our learning plan, our focus for this week is on creating confidence intervals for the difference in two means, as we can see right here. We'll be working on that both today and on Wednesday. And I do have a quiz planned, quiz 9, in S22 for our last 2 weeks worth of material. That's hypothesis testing for the difference in proportions. That's from last week. And then this week's material, confidence intervals for the difference in two means. That should be our second of 2 quizzes from when we started going online. If you've yet to complete quiz 8, a reminder that that still needs to be done, and I'll be kind of reaching out to a lot of people via email tomorrow. Hopefully you can get a time put together with me for you to make that up. Before I go any further, are there any questions on just kind of some general procedural things before we start the lesson? Go ahead and take yourself off mute if you need to speak up. All right, well, hearing nothing, I will go ahead and keep going. All right, so like I said, we've got a couple of sample questions here for the difference in two means when it comes to making confidence intervals. So looking at this question here. Dietitians are trying to determine whether a new low-fat diet actually helps obese people lose weight. 50 randomly assigned obese people are assigned to group 1 and put on a low-fat diet. Another 50 randomly assigned obese people are put on a diet of approximately the same amount of food, but not as low in fat. They're kind of the control group, same amount of food, but not the low-fat diet in question. After 4 months, the mean weight loss was 9.31 pounds for group 1 on the low-fat diet, with a standard deviation of 4.67 pounds, and 7.40 pounds for group 2 on the control diet. Their standard deviation was 4.04 pounds. What is a 99% confidence interval for the difference in weight loss between the diet group and the control group? So a couple of things here. I'm going to assign some names to these groups. Let's call group 1 the diet group, those that were put on the low-fat diet. I'm going to call group 2 kind of the control group. You could mix these around. You could switch these up and call group 1 the control and group 2 the diet. It would just mean that your confidence interval that we're going to generate here in a second is going to be the exact opposite. It'll be negative rather than positive. So putting this kind of setup in place, we have some data to assign. Group 1 had an average weight loss of 9.31 pounds with a standard deviation of 4.67 pounds. So X bar for group 1, the sample mean when it comes to the weight loss, was 9.31 pounds. The standard deviation in that mean was 4.67 pounds. Group 1 had a frequency, a sample size of 50 people. Okay, now let's do group 2, the control group. If I read this here, group 2 had an average weight loss of 7.40 pounds with a standard deviation of 4.04 pounds. So the sample mean in group 2 was 7.4 pounds. That should be S1. And then S2 here The standard deviation for group 2 was 4.04 pounds. And then the frequency count sample size for group 2 is also 50 individuals. All right, continuing on to the next page. Our formula for the difference in two means and their confidence intervals is x bar 1 minus x bar 2. That should be the difference in the two sample means, plus or minus some critical t-score. And in this case, it's going to be a 99% confidence interval. So I need the t-score for a 99% confidence interval with a specific number of degrees of freedom times the variance. So this would be the combined variances of group 1 and group 2. That would be S1 squared divided by N1 plus the sample standard deviation in group 2 squared divided by N2. Since we're talking about means and sample means, we need to discuss the number for the degrees of freedom. Degrees of freedom is typically one less than the sample size for each group. And I have two groups at play, both the low-fat diet group and the control group. Here's the number of degrees of freedoms for the low-fat diet and the number for the degrees of freedoms for the control group. Now, I can obviously simplify this as sample size group 1 plus sample size group 2 minus 2. The -1 and -1 becomes -2. We have two groups, so I'm taking away 1 degree of freedom twice. Questions so far? This is kind of a good place to pause here after I get the whole setup put together. If you have a question, go ahead and take yourself off mute and let me know. That'd be my dog in the background, so sorry about that. All right, let's go ahead and put this together here. X bar 1 minus X bar 2 is 9.31 minus 7.4. Plus or minus the margin of error. Now this t-score, where can I find this t-score? Well, for our example, we have a sample size of 50 plus a sample size of 50 minus 2. That's 100 minus 2, or 98 degrees of freedom. So there's a couple things that we can do. If you have your t-table, I can get an estimate when it comes to the degrees of freedom. I want a 99% confidence interval, and 98 is pretty close to 100. Not going to be much difference between the degrees, the t-score for 98 degrees of freedom and the t-score for 100 degrees of freedom. So in this row, I'll go all the way over, and I see about 2.6 0.26. It would certainly be fine to use that t-score to make this confidence interval. Another example, another option here to get that t-score is to use Google Sheets. And I'll show you that. We're trying to make a confidence interval where I estimate the true difference in these two means. So I take a sample and I want to be 95% certain that I've captured the true difference in these two means for our groups. That leaves me 2.5% in each of the two tails. So what is that t-score that fits this distribution? Well, I can see that there's 97.5% of the distribution below this t-score. So on Sheets, I can type in some cell equals t.inv. And that's going to give me the t-score for a specific probability. In our case, that's 0.975 with 98 degrees of freedom. Oops, it was a 99% confidence interval, wasn't it? That's why we've got a difference here. Let me switch this around a little bit. My apologies. I'm so used to doing 95 when I have to do a 99. Sometimes I forget. Anyway, this is a 99% confidence interval. So we have a 0.5% in either tail. So let's change this coding on Sheets to 99.5. The reason is that there's now 99.5% of the distribution to the left of that t-score. And I see, yep, about 2.627, which is really no different than the one that we got right here. It's off by about, I don't know, 1,000th from our t-table estimate. Times the square root of the combined variances. For group 1, we had a standard deviation of 4.67. We'll square that and then divide by 50. Plus, for group 2, the standard deviation was 4.04. We'll square that and then divide by 50. Questions here at all before I start getting this typed into a calculator? Okay. I need 9.31 minus 7.4. Okay, that's a difference in our sample means of 1.91. plus or minus the margin of error, which was 2.627, times the square root of 4.67 squared over 50, plus 4.04 squared over 50. Margin of error looks like 2.294. So the average weight loss between the two groups is 1.91 pounds with a margin of error of 2.294 pounds. So the true weight loss average between these two groups is no further than 2.294 pounds away from 1.91 pounds. And we'll need to add or subtract to create the total confidence interval. So 1.91 minus our margin of error is negative 0.384. And when I add the margin of error, 4.204 pounds. Okay, so to interpret, we are 99% confident that the average weight loss for the low-fat diet is between negative 0.38, 384, and 4.204. What this really means is that, sometimes I might actually gain weight. The opposite of losing weight is gaining weight. So sometimes I might actually gain 3.84 pounds or lose 4.204 pounds. You could also rephrase your interpretation in that way. 99% confident that the average weight difference for the low-fat diet is 0.384 pounds gained to 4.204 pounds lost. Each of these two interpretations are essentially saying the same thing. Questions there, please? Okay. One more thing. Since 0 is in this confidence interval, since I have a negative and a positive endpoint in my confidence interval, 0 is somewhere in the middle, I'm not necessarily certain if the diet works. Sometimes you're gaining weight, sometimes you're losing weight. So, we can't be necessarily sure that this diet is actually doing what it's intended to. All right, let's try another one. I believe this is actually just number 19 off of the S22 practice. Got a little bit bigger. Okay, so number 19 here says, a man who moves to a new city sees that there are 2 routes that he could take to work. A neighbor who has lived there a long time tells him that Route A will average 5 minutes faster than Route B. Get you there a little bit faster, a little bit quicker. The man decides to make an experiment. Each day he flips a coin to determine which way to go, driving each route a total of 20 days. He finds that Route A takes an average of 40 minutes with the given standard deviation of 3 minutes. And Route B takes an average of 43 minutes with a standard deviation of 2 minutes. Histograms of travel times for the routes are roughly symmetric and show no outliers, so therefore we can do some inference on the data. Find a 95% confidence interval for the difference in commuting times on average for the 2 routes. So let's go ahead and assign Route A and Route B. I'm going to call Group 1 Route A, and Group 2 Route B. For Route A, we have some data here. Route A takes an average of 40 minutes with a standard deviation of 3 minutes. So the sample average in commute time for Group 1 or Route A is 40 minutes with a standard deviation of 3 minutes and a sample size of, let's see, I think he takes each route 20 days. For Group 2, that would be for Route B, I see an average commute time of 43 minutes and a standard deviation of 2 minutes. And he once again drives both routes 20 times in total. Okay. Once again, we need a 95% confidence interval. And we'll use a formula similar to what I've got right here. It is worth mentioning the number of degrees of freedom for this experiment. Since I have 2 different samples, my total degrees of freedom is the sample size of each group, n1 plus n2 minus 2. Let's go ahead and write that down here. Degrees of freedom would be 20 plus 20 minus 2. So therefore, our degrees of freedom would be 38. I have 2 samples, so for the total degrees of freedom of the 2 samples, It's each sample size added together minus 2. All right, so let's see here. Our total confidence interval will be the difference in our two means, 40 minus 43. Plus or minus the margin of error, which is some t-score. Now, I want a 95% confidence interval. So if I draw the distribution, I have my sample mean, and I want to be 95% certain that I've captured the true difference in our means. So here's 95. Here's 2.5. Here's 2.5. What is the t-score? Where 97.5% of the data is to the left of that cutoff. Once again, we have 38 degrees of freedom. So I can use my t-table and get an approximation. 40 is pretty close to 38. And so if I go over to the 95% confidence interval t-score, I see a t-score of about 2.021. I can do the same thing on sheets and get the exact t-score, which would give me a more approximate confidence interval. Equals t dot inv of 0.975 and 38, 2.0244 if I round up, 2.0244. Which was pretty close to what we saw on our t-table right here, only off by a couple thousandths. Times the square root of the variance, which is S1 squared divided by N1 to start. So let's see here, 3 squared divided by 20. And then for group 2, root B, 2 squared divided by 20. All right, let me pause here. Was there any questions on kind of getting this set up so far in terms of using the formula, finding this t-score to make your margin of error? If you have anything, please speak up. Go ahead and take yourself off mute. Be happy to answer any questions right now. Okay, hearing nothing, let's go ahead and continue. Let's see, the difference in our two sample means is 40 minus 43. Plus or minus. All right, I'm gonna go ahead and need a Google or a Desmos calculator for the rest. 2.0244 times the square root of, let's see, I think it was 3 squared divided by 20 plus 2 squared divided by 20. .632 for our margin of error. So our estimate of time says that route A is 3 minutes faster, and that's no more than 1.632 minutes away from the true difference in commute times between the two routes. So for our overall confidence interval, we'll just do our estimate of -3 plus or minus the margin of error of 1.632 minutes. So -4.632 to -1.368 if I round up. For our overall confidence interval. When it comes to the interpretation, we are 95% confident that the commute time for route A is between 4.632 minutes to 1.368 minutes shorter than route B. Let's see, back here on this question, part B. Should this man believe the old-timer's claim that he can save an average of 5 minutes a day by always driving route A? Well, our data doesn't quite support the claim. 5 minutes shorter is not in this confidence interval. The best he can do by our estimate is 4.63 minutes shorter. So I would say no. He cannot save 5 minutes by taking route A. Our estimate says that the best he can do is 4.632 minutes shorter by taking route A. Questions there, guys? Okay. One more thing. I'm going to go ahead and send out a review guide later this afternoon for your quiz on Thursday. We can take a look at that or any other practice problems from S22, the document posted on Schoology with some good practice questions over this material would also be a good place to start in terms of doing some study. I'll get that study guide sent out to you later this afternoon for you guys to practice and check your work on. Was there anything else that we needed to talk about? Any other questions anybody had? for the good of the cause. Okay, I will also make this recording available too, and get that sent out as well. If there's nothing else, have a good rest of your afternoon. See you guys. Take it easy.